Hey, welcome back. The topic for today's lecture and for this week is the syntax and semantics of propositional logic. So as my old math professor used to say, now we're really cooking with gas. You've learned a lot this semester. You've learned the fundamentals that are required now to really understand various logical languages and their semantics. The simplest of the logical languages that we use every day in computer science is called propositional logic. And you're already familiar with it because it's basically equivalent to the language of simple Boolean expressions of the kind that you typically find in while, loop, and conditional statements. So here we go. We're going to talk first a little review, and then we'll dive right in. So this quick review is meant to kind of remind you and to summarize critical material that we've covered so far. So when we're defining the syntax and semantics of a language, what are we really talking about? Well, when we talk about syntax, we're talking about a set of symbols, a set of strings, as it were. And we think of these as not really having any particular meaning. They just have sort of rules that they have to follow to be syntactically well formed. That's what we mean by syntax. When we talk about semantics, what we're talking about is meanings that we give to those symbolic or syntactic expressions. So expressions live in what we call a syntactic domain, and corresponding meanings live in what we call a semantic domain. You can think of the syntax of a language as a set of strings, all of the syntactically valid strings in that language, and you can think of the semantic domain as some other set of values and operations that we use to express the meanings of the terms that we define as being syntactically valid. So looking at the sub-bullets, syntactic terms are defined by data types, data values, function definitions, and semantic meanings are defined as other domains of objects. So in typical practice today in computer science, particularly in the field that you'll learn about in the future called design and implementation of programming languages, we generally represent sets of syntactic terms. In other words, the grammar or the syntax of a language we define as an inductively defined type or as an inductive data type. In other words, if we're thinking about Python programs, for example, each syntactically correct Python program is a value of a type. And that type defines what set of strings constitute syntactically correct Python programs. Okay, so we define the syntax of a language with typically one or more inductively defined data types. If we want to talk about the semantics of such syntactic expressions, we actually have a couple of different ways to do that. One that we've seen so far in this class and that we're pretty much going to stick with for now is that we can define a function that takes a syntactic expression and maybe some more information like an interpretation of the variable expressions that can appear in that syntactic expression. We define a function, an evaluation function, that takes an expression and maybe more information like an interpretation, and that returns the meaning of that expression under that interpretation, where the meaning comes from the semantic domain. So, for example, we defined a language of arithmetic expressions last week and a semantics for that language, so that given any arithmetic expression and an interpretation explaining what number each variable is associated with, we can reduce an arbitrarily complex arithmetic expression to its numerical value. And the numerical value lives in the semantic domain of ordinary, everyday, natural number arithmetic. Okay, so we represent sets of syntactic terms as the values of an inductively defined data type. We define typically some other algebraic structure, or we're given some other algebraic structure, like the arithmetic of the natural numbers. We use that as a semantic domain. We define functions then that associate syntactic terms with things in the semantic domain, with natural numbers, for example, or with operations on natural numbers like addition and so on and so forth. And that's how we define the syntax and the meaning of language. In some sense, you're already now qualified as an entry-level programming language designer. Really, it's true. You've learned a lot. Okay? So, yeah, there's something very fundamental about what we're doing here, right? As computer scientists, we basically invent symbolic representations of things in the worlds that we care about. And then we use those symbolic representations, or better yet, a computer manipulates them in order to derive new knowledge about things in a semantic domain. It's very cool. So, the walkaway message really from the first part of this class is that we can use these capabilities that we've learned about in Lean, like inductive data type and function definitions, but we can use them in very specific ways to define the syntax and the semantics of formal languages. We've done that now for a couple of simple formal languages, including a formal language of arithmetic expressions, and that's pretty good. That's a real advance. Okay, so the third major bullet, if a syntactic domain is defined by an inductive data type that describes the expressions, the forms of expressions that you can use in a given language, then a semantic domain is typically, or can be, an algebraic structure, like the algebraic structure of the natural numbers, with the ordinary operations of addition, multiplication. A different algebraic structure is the algebraic structure of Boolean algebra, as you've seen. So that's an algebraic structure where the set of values isn't an infinite set of numbers, it's just a set of two values, true and false, and a set of operations on those values like and or and not. So in some sense, where we're really headed for is to see that the language of propositional logic is really not much more than, and in fact is deeply equivalent to, a language of Boolean expressions. Okay? It's really as simple as that. So what we're going to do now, and it's going to be even easier than what we did with arithmetic expressions, is we're going to define a little language of Boolean expressions where we have a syntax for defining what expressions we can use and an interpretation function that, given any expression in this language, we'll call it propositional logic, given an expression in propositional logic and given an interpretation for the variables that appear in such an expression, we can then evaluate that expression to derive a Boolean meaning for it, either true or false. Okay, this is George Boole's deep and profound insight that we can give meaning to a logical language by relating it, by mapping it, by interpreting it as corresponding to an algebraic structure. So George Boole, the inventor essentially of Boolean logic, gave us this great gift of understanding that we can define the semantics of a formal mathematical language of Boolean logic in terms of what we now, of course, call Boolean algebra after George Boole. Okay, so let's get going. Let's look at the syntax and then the semantics of propositional logic. And every time I say propositional logic, just think to yourself, okay, that sounds complicated, but really it's just the language of expressions, the language of Boolean expressions. Okay? So this should feel very comfortable and familiar to you now. Propositional logic is a formal language with literal expressions, variable expressions, and operator expressions. And if we're using convenient infix notation for the operators, then we may need parentheses. Okay. So the literal expressions in propositional logic, I will call p true and p false. Now remember, these are sort of meaningless symbols at this point. We haven't imbued them with an interpretation, with an evaluation function. We're not saying what they mean. These are just the two literal expressions. Of course, you can see where we're going with this. P true is going to evaluate to Boolean true. P false, the symbol, the syntactic symbol P false, will evaluate to Boolean false. And just as we've seen in other languages for which we've built these sorts of formal definitions. The second piece of the syntax of propositional logic is that it's equipped with an infinite set of variables. Now you can think of naming them, with nice names like X, Y, Z, or maybe Kevin is from Charlottesville. That's kind of a long identifier, a long variable name. Or, Nifty is a cat. That, all glued together, just one kind of big phrase. That's a variable. So you can see that variables we can give names to variables that sort of express what in our minds are kind of meaningful propositions. Kevin is a cat. It's just a variable at this point. It's just a variable name, not a one-letter variable name, a longer variable name. But it also helps us to think that, what we're going to mean by this variable is some claim, some proposition about something in the world to be, that is either true or not true. Okay, so we have literal expressions, we have variable expressions, and in propositional logic, we have operator expressions, where we can build bigger symbolic expressions, bigger syntactic expressions inductively out of smaller syntactic expressions. Okay, so if E1 and E2 are any expressions in propositional logic, then we can build bigger expressions by connecting those two smaller expressions, whatever they are, E1 and E2, into a larger expression by using what we can call logical connectives. But just think of these as operators. They take expressions as arguments and yield larger expressions as results. So if E1 is an expression, then P naught is a larger expression, where P naught we think of as a kind of unary connective or a unary operator in the syntactic domain of propositional logic. If E1 and E2 are arbitrary propositions in propositional logic, arbitrary expressions, then P and E1, E2 is such an expression. Now, on the right-hand side, I've written the sort of usual infix or prefix notations that most people will be using in everyday practice to represent the corresponding expressions. So P naught E1, go over to the right a little bit and you see that funny negation symbol. We read that expression as not E1. Okay, so that funny little sideways check mark thing is the symbol for negation. It's really a syntactic symbol. It doesn't yet have any semantic meaning, but think of it as a unary operator. You give it an expression, it gives you a bigger expression back, and we write that bigger expression as not E1. Similarly, that tent-shaped operator is the usual infix notation for the propositional and connective. And when I use connective here, you can see why, because it connects two smaller expressions into a larger one, but you can also think of it as just an operator. Just think of it as, we're going to implement them as constructors, but it's just an operator that takes two expressions and gives you a bigger one, builds or constructs a bigger expression out of two smaller ones. So P or E1, E2 is also an expression. P impl, where impl is short for implies, E1, E2 is also an expression. And P equiv, E1, E2, sometimes written as P if IFF, P if IFF, PIFF is also an expression, P if E1, E2. And on the right-hand side, we see the logical notations. You should memorize these logical notations at this point. You need to become fluent in the use of these logical notations to represent concepts in the semantic domain that we'll get to shortly. So let's go down that second column there. We have not E1, E1 and E2, E1 or E2, E1 implies E2, E1 is equivalent to E2, or we can also say E1 if and only if E2. Okay, and remember, these are just syntactic strings of symbols at this point. This is a language in the sense that we've defined an infinite set really of strings, because we can always build up larger and larger ones no matter what we start with. But we don't have a semantics, a meaning for these strings yet. That's going to come next. Okay. The last bullet, sometimes if we're using the infix notation, we need to use parentheses to disambiguate operations. So for example, I have this proposition here. I put a exclamation point at the end, that is not part of the proposition, okay? That's just meant as a, yay, hooray, we understand what we're doing here symbol. But the rest of what I've written there is a proposition. It says it's not, I would read that as, it's not the case that the expression on the left is equivalent to the expression on the right, where the expression on the left is E1 and E2 or E3, where we will compute E1 and E2 first, and then or the result with E3. Now we're getting to the semantics. That's not equivalent to taking E1 anded with the result of computing E2 or E3. Okay, so this example is only meant to show you that you can build larger and larger and larger expressions out of smaller and smaller ones, and this single slide captures the entire syntax of propositional logic. It's a very simple language, but it's really, 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 really important to understand it and its semantics in order really to fully grasp what we're aiming for coming up soon, which is the syntax and the semantics. We won't formalize them, but we'll understand how to use them. The syntax and semantics of predicate logic, and that's the language of sort of everyday mathematics and computer science. But this is the foundation for moving into predicate logic, so good. The good news is the syntax of propositional logic is super simple. You could go off right now and write an inductive data type definition based on what you've already learned called, PX for propositional logic expression that captures this entire syntax, and I think you'd probably get it right. In fact, you might want to pause the video and go try to do it yourself. I'm actually going to work it out for you later, but give it a try. I think you know how to do this already based on what we've covered for arithmetic expressions, or AEXPs. Again, here are some simple examples of syntactic expressions in this language. P true, right? That's at the top. It's a literal expression. X, that's an expression because it's a variable expression. So we have that P2 is an expression and X is an expression. So we can build a larger expression out of those two smaller expressions. And I've done that here on the third line, P and P true X, where P and is a connective that takes two smaller expressions, P true and X, and the result of applying P and to P true and X is a larger expression, a larger proposition, usually written in this style that you see on the right-hand side of the screen, P true and X. Okay, P true and X, we've now constructed it as a larger expression, so we can combine P true and X, take P true and X as E1 and as E2, and combine those two expressions into an even larger expression, which I do on line 4. And let's see, what do I do on line 5? Oh, I just write that same expression using prefix rather than infix notation. Okay, so the middle operator on line 4, the one between the two larger expressions, is the and at the beginning of the line down below, and then the left and the right expressions, P and true X, P and true X, are the things to the left and the right of that infix operator on line 4. Okay, so stop the video for just a second. Let this material kind of, sponge into your brain. I hope you're all jumping up and down now saying, yeah, I got this. This is not so bad. Okay, so you should feel really good about this, because if you feel confident that you're following along here, then you've made a ton of progress in understanding formal languages and logics, and that's a key piece of this course. Okay, so now on to the semantics of propositional logic. Remember, a semantic should give a meaning to each expression in a language, at least where we are in this course right now. When we get to imperative programming languages, something we're not going to touch on in this course, but when you get to imperative programming languages like Java or Python, not every expression has a meaning. Not every syntactically correct program has a meaning. Why? Well, the answer is that some programs can go into infinite loops. And if a program that's syntactically correct goes into an infinite loop, that means it doesn't reduce to a meaning. So the evaluation function for imperative languages like Java and Python is a partial function, which is to say only some of the expressions in the syntactic domain have corresponding meanings in the semantic domain. And that fact complicates things quite a bit. It means that we can no longer use functions in Lean to define semantics. We have to do something else. And the something else that we have to do is actually use predicate logic. Okay, we're not going to get there in this class, but you can see that what this class is going to do is give you the tools that you need to reason about all kinds of discrete structures, even including programs written in imperative languages like Java and C++ and Python. For now, though, the semantic domain and the semantic evaluation function for propositional logic is much simpler. Okay, so here's the basic idea. We'll call an expression in propositional logic a proposition, okay? Let's take a variable x. Instead of using a kind of abstract variable name x, why don't we use something much more descriptive like Nifty is a cat? Okay, Nifty is a cat can be understood as suggesting to us in our minds that what this variable is going to mean to us is the claim that something called Nifty really is a cat. Okay? And the semantics of that expression are going to be either true or false, corresponding to the cases where we, in the world, in our kind of mental mapping of that variable, Nifty is a cat, to what we're thinking in our mind, we want to know whether that proposition is true or false. Now, whereas in predicate logic, we can actually interpret symbols as meaning things like cats. The only thing we can do in propositional logic is interpret symbols, interpret variables, for example, as meaning either true or false. That's it. Okay? So it really is like Boolean algebra. A variable expression in Lean means either true or false. The literal expressions, p true and p false, mean either true or false. P true is going to be taken to mean true. P false is going to be taken to mean false. And a larger expression means either true or false. And the way that we determine what the meaning of a larger expression is by breaking it up into its smaller expressions, figuring out what they mean, and then combining those Boolean values using a Boolean function corresponding to how those smaller expressions are glued together. Okay, so we're going to define bullet number 2 here. We're going to define a semantics for propositional logic by defining an evaluation function, just like we've done before, we'll call it p-eval for proposition evaluation. And the semantic domain of propositional logic is just Boolean algebra. It's just that algebraic structure. Okay? In other words, going on to the next bullet, expressions, whether they're literal expressions, variable expressions, or larger expressions in propositional logic, simply have Boolean values as their meanings. So our p-eval function defines an interpretation for every expression in propositional logic. And in order for this p-eval function to work, it's going to need a smaller interpretation for the variables that appear in a given proposition or propositional logic expression. Okay, because otherwise you don't know what the variables in such an expression mean, whether they mean true or false. Once you know the true or false meaning of each variable in a propositional logic expression, then all the rest is just combining those true and false values using the Boolean operations that correspond to the operators p and, p not, p or, used to build up the larger expressions. Okay, so the final bullet, p-eval, takes a proposition, a syntactic expression, and an interpretation for the variables, just like we've seen for arithmetic expressions, and returns a Boolean value. It tells us whether an expression, a proposition, is true or false under a given interpretation. And remember, again, such an interpretation is simply going to be a function from variables to their corresponding Boolean values. Okay? And there are many interpretations for any given set of one or more variables. So here's a simple example of an application of the p-eval function to evaluate a particular propositional expression or given proposition under a given interpretation. So here on line 1, we see we're applying the p-eval function, which again, in essence, gives us or should give us an interpretation for every expression in the language. We're applying p-eval to an expression in red, x and y, under a given interpretation where the variable x is interpreted as meaning false and the variable y is interpreted as meaning true. Okay? And this expression, as you can imagine, we want it to, and if we define p-eval correctly, it will evaluate to false. So why is that? Well, let's think about how we evaluate that expression p and xy. First, we want to pull it apart into its sub-expressions. So we have an operator, p and two expressions. E1 is the expression x, and E2 is the expression y. E1 is a variable expression, just x, and x evaluates to ff, to false, under the given interpretation. Similarly, the y expression evaluates to tt under this interpretation function that we've represented here in blue as a function that maps x to ff and y to tt and all the other variables to values that we don't care about. Okay, so E1 reduces to false, E2 reduces to true. P and is a symbolic operator. It connects expressions in our syntactic domain, but we interpret it as meaning the Boolean and operation in the algebraic structure of Boolean algebra. Okay, so we have evaluated x to be false, y to be true, p and to mean the Boolean and operator. We now compute a meaning for the large expression p and xy by applying b and to the meaning of E1 and the meaning of E2, which are x and y, which are ff and tt. So we apply b and to ff and tt in the semantic domain, and that, of course, evaluates to false by the definition of the Boolean and operator, which we've already studied. And that's how it works. Okay? The meaning of an expression in propositional logic is composed from the meanings of its sub-expressions, if any. So literal expressions don't have any sub-expressions. They just evaluate to true and false directly. Variable expressions don't have any meaning at all unless you provide an interpretation that associates variables with Boolean meanings. And then the meaning of a variable is simply found by applying the interpretation, the variable interpretation function, to the variable to get a Boolean meaning. So there's no sub-expressions there. But for operator expressions or for connected expressions in propositional logic, the meaning of such an expression is computed from the meaning of its sub-expressions combined using the Boolean operator that corresponds to the connective used to build up that larger proposition, that syntactic string. Okay, so at this point, I believe many of you would actually be able to go off right now, and let me go back to the last slide. I bet many of you would be able to go off right now and write a semantic evaluator for your formalization of propositional logic as we've described it so far. Give it a try. Stop the video here, and if you're curious and not too worried, go give it a try. You now know enough to do what you need to do. Okay. Come back and I'll give you more details. And after the next slide, you really ought to be able to do it on your own. But worry not, we're going to do it for you anyway in the next video. So here's a more complete, more rigorous definition of the semantics of propositional logic. So suppose that EXP is a proposition and interpret is an interpretation, okay, for the variables associating variable expressions with Boolean values. Then we define the p-eval function applied to an expression and an interpretation by cases. Okay? And the cases correspond to the different ways in which an expression can be constructed. If an expression is a literal expression, so for example, if it's p true, we kind of ignore the interpretation and just return true. P-eval applied to p false and an interpretation ignores the interpretation and just returns false. If I said false on the previous line, I meant true. So p-eval p true interp ignores the interpretation because there's no variables in this expression and just returns true. P-eval p false interp ignores the interpretation because there's no variables in this literal expression and just returns false. Now, if p is a variable expression, in other words, something of the form like var x v, where v is a variable, just as we did in for arithmetic expressions, then evaluating that variable expression under a given interpretation returns the result obtained by applying the variable interpretation function to the variable v. And again, this is just like we did for numeric values in arithmetic expressions, but now we're dealing with the simpler case of Boolean algebra and Boolean expressions. Finally, if EXP is a connective expression, such as E1 and E2, then we look up the Boolean operator. So look up the logical connective. This operator is P and, okay, propositional and connective. We look up the corresponding Boolean operator, which would be B and. So we need to have a little interpretation function for the connective symbols in our logic as well. So here we would apply, as it were, the connective interpretation function, the operator interpretation function, just like we did in arithmetic expressions, to find the corresponding Boolean operator in the semantic domain. Here it's B and. Then we recursively evaluate E1 and E2 under the same interpretation to get Boolean values for E1 and E2, and then we simply combine those Boolean values using the Boolean operator that corresponds to the connective in our expression. Okay, and the same idea applies for unary operators like not, but we just recursively evaluate one sub-expression instead of two because the not connective applies to just one propositional expression rather than two. Okay, so here are some examples, and these are in the style in which we presented some of the earlier work. So suppose we have variables named v0, v1, v2, and so on and so forth, and we have variable expressions built up using a var exp constructor in our propositional logic inductive data type. If you're not quite following that, stop the video and go back and look at how we implemented arithmetic expressions and arithmetic variable expressions in particular. Think of a literal expression, well, think of a variable expression as kind of a box containing a variable. To evaluate it, we'll open the box, we'll pull out that variable and apply the interpretation function to it. Okay, so suppose that we have variable expressions now, x, y, and z, and we have an interpretation function that looks like this. If you apply this interpretation function to the x variable expression, pardon me, this is actually wrong. An interpretation function would apply to v0, v1, and v2. This is a bug on my slide. I'll fix it before I post these slides. An interpretation function maps variables, not variable expressions, to Boolean values. So, in your notes, this should be v sub 0, v sub 1, and v sub 2. Okay? So if we have an interpretation that takes v sub 0 to true, v sub 1 to true, and v sub 2 to false, now suppose that we have this propositional logic expression, the x proposition, the y proposition, not applied to the y proposition, and then and used to combine those two smaller propositions into a big proposition that we would read as x and not y. The question I'm going to ask you is this proposition true under this interpretation? Okay. Well, to find out, let's apply our formula. Okay. We ask ourselves, what's the main connective here? And it's and. So we know we're going to use b and to combine the Boolean values of what x evaluates to and what not y evaluates to. Let's see what x evaluates to. Well, x is a variable expression with v0, and v0 is going to evaluate to true, so this is going to evaluate to true. Now we have to evaluate the expression not y recursively. Now, evaluating not y involves recursively evaluating y, which is var x v1, and v1 under the variable interpretation also maps to true. The not connective maps to b not. So this whole thing evaluates to be not true, which is false, or FF in lean. So we now have b and true, false, which is false. So this whole thing ought to evaluate to false if I've got everything right here. You can double check me, okay? So you can see that the way that we determine the meaning of a compound expression is by recursively determining the meanings of its parts and then combining those meanings using an appropriate operator in the semantic domain. Okay, so this is just more detail explaining how all that evaluation is done, and I believe that I've made the same type error on the slide here. Lean would have caught me if I had done this, drawn this directly from Lean, but this just goes through what I just explained in more detail. Okay, so down at the bottom, what I've written is something that I hope makes life a lot easier for you. Boolean algebra is the semantic domain of propositional logic. And propositional logic is really just a syntactic language for writing down formulas in Boolean algebra. Okay? If you're a logician, you would say a couple of different things. You could say that, the syntax of propositional logic is isomorphic to, the set of legal expressions in Boolean algebra. You could also say Boolean algebra is a model for propositional logic, or you could just say that Boolean algebra is the semantic domain in the form of an algebra or an algebraic structure for the syntactic language of propositional logic. Stop the video and, go back and rewind and listen to that again a few times and just recite it a few times, right? So you could say, for example, yeah, Boolean algebra is the algebraic semantic domain for propositional logic. Say it 10 times, and you'll not only feel it as an understandable and true statement, but you can repeat it at cocktail parties, and people will just melt because they'll be in awe of you. It's true. Okay, so we now have a new language. We haven't implemented it in Lean, but that'll come next. Our new language is the language of propositional logic. We'll give, and that language has a meaning, has as its meaning really the algebra of Boolean values. So George Boole's great insight was that logic, which previously had been kind of a humanities-ish topic, suddenly becomes a mathematical topic. So George Boole gave us the great gift of what today we call mathematical logic, where the semantic domain of a given logic is some algebraic structure or another. Okay, and there are many different forms of logic, each with its own kind of back-end algebraic structure providing its semantics. Good. So you understand the syntax and semantics of propositional logic now. And the last thing that I want to talk about, and it's a really important topic, is to begin to get a tiny little bit of practice converting English or natural language thoughts into propositional logic and back. Okay, so I'm just going to give you one little simple example here. And this particular example is meant to highlight the point that you actually have to be a little bit careful in how you translate kind of natural language statements into logical formulae. So suppose I have two propositions. They got married is one, and they had a baby is the other. And I don't mean to get into complex issues of social mores and so on and so forth. And if you find the example slightly inappropriate, sorry, but I find it slightly inappropriate too, but also compelling. Now, here's the question. In English, are the following two connected propositions, do you feel them to be equal in meaning? They got married and they had a baby. They had a baby and they got married. Not every family, I guarantee, would read those statements as being equivalent in meaning. And the reason is that the word and, as used in these statements, has a slightly different meaning than it does in Boolean algebra, right? In Boolean algebra, and is commutative, which means if x and y is true, then y and z is true. And if x and y is false, then invariably y and z is false. In other words, x and y is equivalent to y and x. X and y and x always mean exactly the same thing in Boolean algebra. But in English, they don't always necessarily mean the same thing. So take just a second and ask yourself, okay, in what sense do the meanings of and differ in propositional logic and in this example here? They got married and they had a baby. They had a baby and they got married. Well, in this case, the and seems to mean something more like and then, in order. One event after another event. First they got married, then they had a baby. Or I should say, first they got married and then they had a baby. They had a baby and then they got married. So in English, that word and sometimes means and then. And then can be formalized in a logic, but then you're dealing in a logic that we call temporal logic. And temporal logic deals with things happening in discrete points or continuous points in time. And we're not talking about temporal logic here. We're just talking about plain old propositional logic for which the underlying algebra is Boolean algebra. And that means that it would not necessarily be appropriate to formalize they got married and they had a baby using the and connective in propositional logic, because if you do that and you judge that sentence to be true, then somebody could flip the events in order. They had a baby and they got married. And in Boolean algebra, in propositional logic, those are equivalent statements, but not in English. So one of the things we really want to do is to begin to get some practice translating English statements into corresponding formulae in propositional logic. And we call this process formalizing, right? Okay, so if I tell you that x is less than 7 and I tell you that y is greater than 8, you should be able to combine those two smaller propositions into one bigger one using an and. X is less than 7 and y is greater than 8. And in this case, it doesn't matter what order you combine those, because if both of them are true, then the combination is going to be true. Otherwise, the combination is going to be invariably false. Okay, so let's be a little careful formalizing natural language in logic, but when it comes to mathematics, things get easier. Okay, so next up, we're going to formalize propositional logic in Lean. As a really, really great exercise, I'd urge you to go ahead and try doing it yourself now. use our implementation of arithmetic expressions as a model for how to proceed with Boolean expressions, i.e. with propositional logic. Okay, you should be able to do this on your own, albeit, might have to work out a few details. Okay, you've seen the syntax and a semantics for arithmetic expressions. We're now just using Boolean values and Boolean operators instead of natural numbers and arithmetic operators. Okay, so propositional logic is Boolean algebra, or a better way to say it is that it's isomorphic to Boolean algebra, or that Boolean algebra is a model for propositional logic. You already understand Boolean algebra from your other programming classes. You've written lots of Boolean expressions as controls for loops or as conditions in if-then-else statements. So all of this should be fairly, not feel too scary at this point. We talk about algebraic structures and interpretations, and it's a lot of fancy language, but this is stuff that should be, fairly comfortable for you to deal with. Okay, so that's what's coming up next. The last thought that I want to give you here is that while it's fairly straightforward to formalize the syntax and the semantics for propositional logic in any such language, the really interesting questions revolve around variable interpretations. Okay, so remember, a variable interpretation gives you a Boolean value for every variable that appears somewhere in an expression. So you could have x's in 3 different places in an expression, and of course, the interpretation will always give you the same value for those 3 occurrences of that variable. But if I have 7, say, distinct variables that I use x, y, z, w, p, q, and r or something in an expression, an interpretation will give me some combination of Boolean values for those 7 variables. Suppose that there are 8 variables. How many different interpretations are possible? Well, for the first variable, there's 2. For the second variable, there's 2 for each value of the first variable, so there's 4. When I look at the third variable, there's 2 values for each of the 4 values preceding, so now there's 8, and you get the idea. 16, 32, 64, 128, 256. If I have 8 variables, there's 256 possible interpretations. And that, too, is a concept that you should be familiar with now. Think about how you'll write an interpretation function. You'll have the variables, let's say 8 of them. And for each one, you need to return a Boolean value. You need different interpretations correspond to different patterns of return values. If I have 8 slots to fill in, and I can fill in each one with either a true or a false, I can enumerate all possible patterns, and the answer is 2 to the 8th, which we can enumerate as 0 to up to 255. And so now the interesting question, here's the really interesting question. If I give you some proposition with those 8 variables in, does that proposition evaluate to true under any of those interpretations? In other words, we're asking you to answer the question, is there an interpretation under which a given expression evaluates to true? That's the problem we call Boolean satisfiability. And it's one of the most fundamental, important, and interesting areas in computer science. It's still a hugely active area of research, and programs that can solve that problem efficiently in practice are tremendously important in computer science. So at this point, or actually when we address this problem, this issue, which we will do after this pair of lectures, you'll understand one of the most important, rich, and interesting areas in all of computer science. And in fact, there's an opportunity here for you. If you can come up with an algorithm that always answers that question in less than 2 to the n time steps, where n is the number of variables, you'll basically go down in history as like Einstein or Gödel. Okay, so I don't recommend you try to work on this problem. Lots of people have. It's very hard. We don't know if there's such an algorithm. We don't know if there's not one. It's a great mystery, probably the greatest open mystery in all of computer science. Okay, so you're now set up in this class to understand some really, really interesting stuff. Okay, the last question, and a related question, is Does every interpretation, does a given expression evaluate to true under every interpretation? An expression for which there's some interpretation that makes it evaluate to true is called satisfiable. If there's no interpretation under which an expression evaluates to true, it's called unsatisfiable. And if an expression evaluates to true under every interpretation, it's called valid. The simplest example of a valid expression in propositional logic is just p true, right? Because it always evaluates to true. The expression x is not valid because x could evaluate to true or it could evaluate to false. So there's one interpretation under which a single value evaluates to true. So that's a satisfiable expression. There is one interpretation, namely the one that associates x with true, that satisfies that proposition. So that proposition is satisfiable but not valid. Here's a proposition that's never valid, x and not x. If x is true, then not x is false, so you have true and false, which is false. If x is false, you have false and not false. Not false is true, so you have false and true, and that's false. So whether x evaluates to true or whether it evaluates to false, x and not x always evaluates to false. So that's an unsatisfiable proposition. And finally, I bet you can come up with an example just involving that one variable x of a proposition that's valid, that's true, whether x evaluates to true or whether it evaluates to false. And that's a hint. So see if you can come up with the answer to that one on your own. It's super easy, okay? Take a little thought, but you'll like it when you get the answer. Okay, that's it for now. Coming up next in the next video, we will go through our implementation of propositional logic, syntax, and semantics by embedding the language and its semantics into the logic, the predicate logic, the constructive predicate logic of the Lean prover. So Lean implements a logic. Yeah, that's what it does. Good. Okay, so until next time.